So we talked about how fixed point numbers allow us to express fractions, but that you have to know where to put the binary point. So now we're going to talk about floating point numbers, and these are what to do when you don't know where to put the binary point. So if you're going to have some numbers that are large and some are small, but you're not sure what the right place for the binary point is, what floating point does is allows us to have the binary point be floating. That is, we can choose where the binary point goes for each number. So let's take a look at that. So fixed point works great if we know the range. So if we know the range of the number, we can choose the right binary point. As we said, this is great in applications that only do one thing, like cell phones, where you're only talking to the base station and encoding signals to send back and forth, but most stuff doesn't know how to do that. For example, if you're processing an image, you don't know if the values in the image are going to be bright or dark, or if you're processing a movie, you don't know if there's going to be a lot of motion or very little motion. So floating point solves this. And the way it solves it is we use some of the bits to choose the binary point. So before we had fixed the binary point, now we're going to take some of our bits and we're going to say those bits determine where the binary point is. So here's an example. We have 20 bits and we're going to use 4 of them to specify the binary point. So here's 16 bits and then 4 points, which we're going to call E for exponent, to choose the binary point. So if our exponent here is 0, 1, 0, 0, or 4, that may mean the binary point is here. It comes after the 4th digit. So now we have a number, we have lots and lots of bits after the binary point, but only a few bits before the binary point. Or if we change this exponent to 12, it's going to shift the binary point way over. So in this version where we put in a 12, we have lots of digits before the binary point, so we can have a very large number, but very few after the binary point. So we don't have a lot of resolution for fractional values. And this is the key to floating point numbers. We're going to use some of the bits to specify in effect where we put the binary point. And the way we're going to do that is these bits here are going to be an exponent. So that exponent is going to multiply these bits, which effectively shifts the binary point back and forth. So if we have a small exponent, we can represent small numbers very well. Or if we have a negative exponent, we can shift it even over further. And if we have a large exponent, down here we can represent large numbers very well. It's worth noting here that a floating point number can't represent both small numbers and large numbers at the same time, because you'd have to have your exponent both small and large at the same time. And we're going to see this as a problem later on in the next segment. So, floating point, we use some of the bits to choose the binary point. You can have large or small numbers by moving the binary point, and this allows us to use more efficient use of our bits. The number we're representing can adjust to the size of the number we need to represent. So here's an example. So here we have our sign bit. So we're going to have one bit to tell us if the number is positive or negative. And this is what we talked about with sign magnitude. Remember, we said we were going to use that in floating point. So we have one bit for that. We have a whole bunch of bits here. These are the significant digits. This is what determines the actual number. This is known as the mantissa or the fraction. And these are the bits that we're going to represent the number with. Then over here we've got an exponent. So we have an implied base. And we say it's implied because we don't store this 2 in the number. Everybody just knows that it's times 2 to the some power. And this over here is the exponent. This is which tells us how much we move the binary point. So 2 to the positive 78 means move the binary point over 78 places this way. So that's going to give us a very large number, much larger than we could represent just with these fractional bits. If it was 2 to the minus 78, it would mean move the binary point 78 places over this way, so we get a very, very small number. So where did this come from? Well, the standard we have today, which is the IEEE floating point standard, came around in the 1980s, and it was basically because everybody who was making computers had their own standard, and they wanted to make sure that you could make portable information, so you could change numbers back and forth between computers and to maximize quality, because getting floating point numbers right is really, really tricky. So here's what they came up with for half precision or float values. We have 32 bits and we use them as follows. The 31st bit, this is the sign. This tells us whether the number is positive or negative. Then we have 8 bits for the exponent. So this allows us to shift the binary point up to 8 bits, so 256 places to the left or right. Then we have 23 bits for the mantissa or the fraction. So this gives us the resolution of what we can represent. So this is the fractional part. And then here's the interpretation. So minus 1 to the s. So if s is 1, it's minus 1 to the 1, which means it's negative. If s is 0, it's minus 1 to the 0, or 1. So this is the sign bit, times 1 dot f. So this big mantissa here, we always interpret it as if there was a 1 before whatever value are in these bits, and then times 2 to the e minus 127. So here's our exponent, and we're subtracting 127 from it. So this is not obvious, and this is why I say this was about maximizing quality. Making a good floating point standard that works well is not easy, and so they wanted to have a standard one. So the two things to note here is this 1. This is a normalized number, and by putting in this 1 here, it means we only have one way to represent every number. We'll see that in a minute. This over here is an exponent bias. So the exponent here is not a signed number, it's an unsigned number, and we get negative and positive by having a bias in here. And this way of representing the bias just makes it easier to build circuits that compare numbers. So, when I said this was really hard to get right, for example, graphics processors have been doing floating points in their own formats for a long time, and it took them until 2008 to start standardizing what they were doing. So even today, people have a hard time with this. Now let's talk about some of the details of floating point numbers. So we have s, the sign bit. This tells us whether the whole number is positive or negative. We have the exponent e, and this is an unsigned value, but we bias it here by 127. So if e equals 127, then we have 127 minus 127, we have 2 to the 0. And then we have the fraction f. And this again is an unsigned value, remember our sign is over here, and it's regarded as a binary value with one dot in the binary point before it. So if f is 1, 0, 0, 0, our number is 1.1 times 2 to the whatever the exponent is. So remember, here's what we had. We had the sign bit, 8 bits of exponent, and 23 bits of fraction. Now let's take a look at some examples. So here's an example. We have 1, 1, and then all zeros. So what this number says is our sign bit is 1, our exponent is 1, 0, 0, 0, and our mantissa is all zeros. So how does this work out? Well, we get this number. We get minus 1 to the 1, here's our 1, times 1.0, here are all of our zeros from our mantissa, times 2 to the 128 minus 127. So this value number is 128. What does that work out to? Well, it's minus 1 times 2, or minus 2. So this number here is minus 2 in floating point. Here's another number. So in this number, we again have a 1 for the sign bit, so we know it's going to be negative. We've got all zeros for the mantissa, but now our exponent here is 127. So now we're times 2 to the 127 minus 127. This is going to be 0. So now we get minus 1 times 1. So this number here is 1. Sorry, minus 1, because we have our sign bit is 1 here. Positive 1 would just have a 0 over here. Here's another example, 0, 0, 1, 1, 1, 1, 1, 0, and zeros. So this is minus 1 to the 0, so this is going to be positive, times 1.0, times 2 to the 126 minus 127. So 126 minus 127 is going to be minus 1, so this is going to be 1 times 0.5, or 0.5.